with more of a focus on artificial intelligence. And it turns out that in both cases, information theory and information geometry. It turns out that in both cases, information theory and information geometry are very useful tools because a lot of probability distributions on the space of possible outcomes of an event are necessary, and thus you have to work in the space of probability distributions over the space you're interested in fundamentally, and then you have to adjust things in that space. Technically, well, I will begin with one of the applications, namely optimization. So, what is called black box optimization, it's a very old problem. So, you have a space X, and you have a function from X to R. X can be basically anything, but it's a space of configuration of an object you're interested in, typically. And the question is to find a point in X such that the value of F is the best possible. And in black box optimization, the only thing you can do is, you don't know a lot of things about F. You can only compute F for a given X. So in a typical situation, X might be the shape of a plane, and F might be the consumption, the oil consumption of the plane for a given distance, and you want, in that case, you would want to minimize it instead, of course. And then what you can do, typically, you can do a simulation. You can try an X, try to compute by your simulation, either a real simulation or a computer simulation, the value of F, and then explore one X, one other X, a third value of X, and then try to guess a hint of where you want to go next for the next value of F you're going to try. And so this problem is quite important in applications, and there are a lot of approaches. The most basic approach to solve this problem is gradient ascent. So if you know the gradient of F, you can try to update the value of F by adding to it the gradient F, and of course, if the step size is small enough, you will improve the value of F. So you will climb to the nearest local optimum of F. But there are several problems with this. First, you have to know the gradient of F. In the black box optimization setting, you don't have access to it. You can only evaluate F. You can only evaluate the function of a given point and not compute the gradient. Maybe you can compute the gradient numerically by taking F at very close points and dividing the difference, but still maybe it's not so reliable, etc. A second, more serious problem, in my opinion, with the gradient ascent is that it depends on a choice of coordinates for X. Here I have supposed that X is implicitly Rn, but the trajectory of the gradient ascent depends on the basis you use to compute the gradient. And this is because this is approximately equivalent to setting so if the new point is x prime equal x plus epsilon times the gradient of F, this is equivalent up to second order in epsilon to setting x prime. Well, what you're going to do is find is jump to the best value of f, penalized. So penalized by the distance from the current ID you have for f. So if you could jump to the best f of x prime, you would have solved the problem, of course, but you cannot do that in general. So what you can do is solve this problem in a neighborhood, because then the problem becomes locally linear, locally quadratic, sorry, and you can solve it if you know the gradient. So what you have is the following characterization of gradient descent. X prime, given by the gradient descent step, is the argmax of f of x prime minus the distance of x prime to the current estimate of x divided by the step size, typically. So what you have is, you have your function f, you have the current x, so the minimum is here, but then you are going to add, this is for minimization, but here I'm maximizing. So you have x, you have the function f, and then you are going to add to f a penalty for not moving too far, and the penalty is going to be like this, very sharp around x, and so the sum of the two functions will have a minimum somewhere. Do I have colored chalk? No. Somewhere close to x, and the sum is going to be maximal somewhere around here. Thank you. And this is where you are going to jump. And the problem with this is, it depends on the choice of a norm. If you change the basis of Rn, on which you're working, you will change the norm. And so you will change the trajectory of gradient descent. So it doesn't matter that much if your function has a unique global maximum, because you're going to end up there one way or another. But if you have multiple optima, and one of them is good and the others are not so good, then the different trajectories, even starting at the same point, can end up at different optimum. And it's important to choose the best optimum, obviously. So it's important to do the gradient descent, if you use gradient descent, using a relevant norm. Because here this norm uses the numerical representation of x, and you are going to choose a basis for your space capital X. You're going to decide that the size of the change in x is the norm, the stupid Euclidean norm, in that basis, computed in that basis, in that numerical representation. For instance, if you have a two-parameter space, for example, if you're trying to sell mobile phones, and you have two parameters, you have the size of the phone, you want the phone to be as small as possible, and you have the number of hours that your engineers spent writing the code of the software in the phone. So if you encode the possibilities by deciding that you measure the size of the code in number of kilobytes of code and the size in inches, you're going to have one gradient. And if you encode the size in millimeters and the number of lines of codes in the size of the file in kilobytes rather than megabytes, or just number of characters and number of lines, it's going to give you a different gradient descent as well. So these are design choices for your problem that you would want any algorithm to be insensitive to. So one possible solution is to turn this problem to another space. And that space is the space of probability distributions on X. So this is where information geometry will come in. So imagine that now what you work on is not X, but is a space, a probability distribution on X. And that what you are going to adjust is the parameters of the probability distribution. For example, if you work on Rn, you could use a Gaussian distribution on Rn, parameterized by its mean and covariance matrix, for instance. So the parameter, I'm going to call it theta. This is the mean and covariance matrix, or any other probability distribution family you could think of. And theta represents, p theta represents the belief you have about where the good points X lie. So, and you are going to explore. So if you start with a given value of theta, you can sample a point X from p theta, sample a few points, look into which direction things seem to be improving, and adjust theta to move into that direction. This originated in the 80s and 90s in the theory of genetic algorithms, actually, because this is kind of, you have a current p theta, you have a current point X, you sample a new point X according to p theta. This can be seen as a mutation of a random mutation of the current value of X, and if it's good, you keep it. If it's bad, you throw it away, and you try a new random mutation, and you adjust the probability, you adjust the center of your distribution p theta. So these emerge from the ideas of genetic algorithms. Now, the problem is how to transfer your original function f from the space of X to the space of theta. So one possibility is to define a new f bar on theta space by saying f bar of theta is by definition the expectation for X following p theta of f of X. And now you can do, you have transferred your problem from X space to theta space, and you can try to optimize on theta. For instance, by using the gradient ascent on theta. Of course, there is another problem, which is numerical evaluation of this expectation. But this you can solve by Monte Carlo samples, by sampling X. So, if you want to do gradient ascent on theta, what could you do? Well, first, as I said, if you are going to use a gradient, you need a metric on theta. So, you can use the standard Euclidean metric. You can say that theta is a list of numerical parameter. It's a list of numbers, and you can use the Euclidean norm on these numbers. But this is not good for reasons that I presented 5 minutes ago. And so you have to build a more intelligent way. So I'm going to rewrite the formula. You are going to have an update of theta. This is f bar of theta prime minus the distance between the old parameter and the new parameter. And here you are going to use another norm, which is the Fisher metric. On theta. So what is this? I guess a lot of people in the room know about it already, but I wasn't sure because of a possible mixed audience in this room. So instead of using a numerical representation of theta as a set of numbers, we are going to define a metric based only on the probability distribution p theta itself. So when you have two probability distribution p theta and p theta prime on the same space, you can define a distance, or at least a divergence between them, by taking the relative entropy. So if you define, if you have p, a probability distribution on variable x, and p plus delta p, another one. So these probability distributions are